Okay, so what we're going to do is we're going to kind of quickly go over randomness, probability, and simulation. I'm going to run through these and kind of interpret some things as we go along. These are the three things that you need to get from this first video. We're on long run frequency, the myths about randomness, and simulation. All right, so basically here's the definition of probability. Any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very large number of repetitions. So if you do it a lot, that's what it's talking about right here, it's the proportion. Remember, like out of 50 times, how many of them come up heads, okay? Then you also have the law of large numbers, which means if you do a lot of repetitions, then eventually, you might remember this right here, do a lot of repetitions, say this is 1, this is 0, if you flip a head or flip a coin, the probability that it flips heads turns out to be really, really close to 0.5 in the long run. All right. You can also do a simulation, which is the imitation of this chance behavior, and it's based on a model that reflects the situation. And remember, there's a 4-step process. 1, you have to ask a question about some chance process. That's the state. 2, you have to plan. So describe using a chance device, let's say like a random number generator or a table of random digits or a calculator, and tell us about the repetition of the process. And then tell what you're going to record at the end of each repetition. Then you're going to do the repetitions, perform it, and then you're going to give a conclusion based on that. Okay, so next, these are some questions that could arise, like explain what the probability of 0.9 means in the setting above. The 8 a.m. train has arrived 5 days in a row. What's the probability that it'll arrive on time tomorrow? Well, since it's already established here, it's 0.9 because each day is independent of the next. A businessman takes the 8 a.m. train to work on 20 days in a month. He is surprised when the train arrives late in New York on 3 of the 20 days. Should he be surprised? Describe how you would carry out a simulation to estimate the probability that the train would arrive late on 3 or more of the 20 days. Well, because you have a 0.9, remember, you're going to use the numbers 0 through 8, and then the number, this is on time, and then the number 9 could be one that is not on time or late. Or you can flip that around and put 0 as your late, and then, of course, 1 through 9 as your on time. So it depends on how you kind of look at things. All right, so here is a dot plot that shows the number of days after we did 100 repetitions. Notice that out of 100 repetitions, what is the resulting estimate of the probability described in question 3? Well, simulated number of late arrivals. Well, 1 happened to have the most, and then 2, late twice, so late 1 time, or late twice, or late 3 times. So this basically, if this is the number of late arrivals, if it's only late once, majority of the time, that kind of plays in favor of the 0.9 of being on time. And then, so this is the conclusion. Again, we talked about long run relative frequency, myths about randomness, and then chance behavior. And we'll continue this as we move along.